This unique shape, and the fuel gets injected in here and then is directed along the inside of that bowl. And just as an example, here's a piston from like a large truck engine. So this is the piston bowl from a large truck engine. This is what's in a locomotive engine. So we're looking at very much larger hardware. The engine that we have going here, single cylinder engine, is 375 horsepower. And to put that into scale, that's about twice as much power as the engine in my minivan. So even one piston generates a lot of power. The full-blown engine will be, the 12-cylinder engine generates about 4,500 horsepower. So you can walk over here. We've got a little bit of hardware out here for you to look at. Again, this is a fuel injector from like an automotive engine. Here's a fuel injector from a locomotive engine. And this is the piston and connecting rod that was pulled out of our engine about 2 years ago. The engine head, and sitting in here is the combustion chamber, where we have the piston moving up and down, compresses and burns the fuel, and then we do we'll do our performance tests on here. This over here is basically a large electric motor that allows us to control the speed and load on the engine, so that we can simulate real engine operating conditions. And usually what we're focused on is emissions and fuel economy. I know it's fun to think about trying to make more power, but really what we want to do is save fuel, because fuel can be very expensive. So generally what we're focused on is very small amounts of fuel economy benefit will be profit for the business. They can sell that to the rail companies, and also meeting emissions regulations. The EPA is always changing the regulations, always trying to make engines cleaner, and so we need to stay on top of that and make our engines cleaner.
Pressurized air. We have the tail end over here where we have the explosions coming out, and this is part of the tube which isn't actually attached. This is an open type tube. It's not contained in one of those gigantic vessels. And then this is a big exhaust tunnel over here which can suck the exhaust gases out of the room so we don't have any dangerous gases in here. So we put air in right here. These are two valves for the fuel. So we'll put a gaseous kind of fuel, kind of like natural gas, but not like gasoline or anything. And we'll inject it into the tube. These are spark plugs right here. So we have an ignition system that creates a spark, just like an automotive kind of system. This is like a spark plug in your car. And then we have, this is a spiral right here. This helps the process along. It helps accelerate the burning. And then all the combustion gases would come out of this tube, and you'd have a big bang.
So watch that from up there too.
Yep. Or typically, when we run this tube, we'll have a camera, like a camcorder, with a little pan tilt zoom attachment, so we can take these things while it's going on. Nice. Now we call this a thrust stand because we can actually measure the output of this tube and how much thrust it's producing. So this whole thing's on. You hear the hissing noise? That's air being pumped into a sliding air bearing. It's meant to reduce the friction on this table, so when this tube fires, we have a reaction force. We have a couple of springs over here, and if we measure how far it moves, we have an idea of how much thrust the tube is producing. So if you want to, you guys can push on the thrust stand and feel.
Gravity works today, right? So rethinking the laws of physics is a chance of a lifetime. You never get to do that. And because of nano and looking at materials at that length scale, we're able to rethink and learn new things and do things we never thought we could do before with materials. And I'm going to show you some examples, all right?
It's already started.
All right. Cool. So you guys are material scientists, whether you know it or not, right? You can get degrees in material science, but you already are material scientists. Because you use materials every day and you know what to expect from them. You know when you should use a metal or a plastic or a ceramic, right? You know what ceramics are?
Yeah, clays.
Clay. You have clay pots, chalk, coffee cups. They're excellent high temperature materials. And you can put a coffee cup in the microwave, in the oven and everything, and it's great high temperature material. It's very lightweight, right? Take a chunk of your coffee cup versus the same size of a metal, it's very light. We'd love to use ceramics all the time, especially in an engine, right? Your airplane would go a lot faster if you could run the engine hotter because you had ceramic instead of the metal, and it was that much lighter weight. But ceramics have a problem. What? They break. They're very brittle material, so you would never, ever want to use them in an engine, or anything that moved anyway. You know, if you take the hammer, a little nudge, it's gone, right? Very lousy structural material. So, we all know ceramics are brittle, that's a fact. Has been for thousands of years. Why does she have this shell? This shell is the same chemical composition of this chalk. 99.99% calcium carbonate. It's got 0.01% of some protein in there somewhere, but it's basically chalk. I could throw this material against the wall, I could throw it on the floor, and I have, but I'm not going to today because I don't like doing it. It's stressful. Stressful. But this has this material even sounds different, right? I can really pound on it and it doesn't break. It's chalk. Why doesn't it break?
Because it's been in the water.
It's
been in the water.
Shapes, right? Looking good.
It's looking mean.
All right. Well then, oxide, iron oxide. Put them in water. What's going to happen now?
Nothing.
Same thing as before. You know, I get my iron filings, making the same cool shapes that they did before, right? So, it's very predictable. It makes a lot of sense. Now, I'm going to make those same particles, change nothing but the size. Now I'm going to have roughly 50 nanometer size, 50 nanometer particles again. So the diameter of the sphere is 50 nanometers, and they're just made up of iron oxide. And I'm going to bring, this is the stuff right there. It's a solution of it, just like we had this. Now I'm going to bring it near my magnet. I cover the magnet in a little glass tube so I don't make a mess.
Whoa.
So,
I think I get this.
what do you think?
So
Did anyone
cool.
predict that? I didn't. Right?
Yeah, you did.
Zooming in.
I
Get all good close.
So I can do it again. All right. Okay.
The graphic that's on the wall.
All right.
I was just thinking that too.
That is the graphic on the wall. It's called a. Okay.
Yes.
So why does it work? You have any ideas?
Because you put nano.
They use the same materials.
Yeah. So why does the nano hairs make a difference, right? And here's my leak. I ran out of water. No, I didn't. Okay. Ran out of.
Just takes it with it.
Takes it with it.
That's so cool.
Imagine you put that on a windshield.
Exactly. They call this self-cleaning. Aluminum. Let's see, different sides of aluminum.
How
Depending-
hard is it to just cover all metals and stuff?
So we wanted to make it super hydrophobic. So this is our aluminum now.
Whoa, it just went bounces too.
That is insane.
So now we're going to use these sorts of coatings and try to make our engines and gas turbines self-cleaning, and we can get, you know.
My name's Roy Primus. My particular background, I work on piston engines. I've been working in the piston engine arena doing combustion performance emissions control of these things for 33 years now. Having done my schooling, I was an undergraduate in mathematics with a minor in electrical engineering. And then I went on and got my master's in mechanical engineering while doing my thesis in chemical engineering. So one of these days I'll figure out what I want to be when I grow up. But the Energy and Propulsion Technologies group here, we're going to talk to you about the kinds of things that we do. Now you saw in Trish's overview that we do have a global research center, and with our Energy and Propulsion Technologies crew.
Do you like your job?
I love my job.